something.
Oh well.
Sure, it was done innocently, so
I'm sure. You think if somebody did that, even if it wasn't, if it was a deliberate act, they wouldn't want anyone to know.
Oh, right. Yeah, that you didn't have the security protocols in place. Yeah, it's just better. It's better it all goes away. There we go.
There we are.
Steve, who used to be Book Davies, but Steve is saying hello. He's saying howdy. Hiya and howdy.
Howdy, Steve.
Howdy. Oh, yeah. Way. Mike Wiesner says hello from very windy but clear southern Arizona. Rex saying hello. Steve says hiya, Doc, Dan, and Scott. Try to say that 10 times real fast. Doc, Dan, and Scott. Doc, Dan, and Scott.
Yeah, we were doing sketching Saturn in my class today.
Oh, cool.
Yeah,
using your quadrant method.
Yeah, this is the kids in the Astronomy for Educators class.
Mm-hmm.
And we were out last week sketching Saturn. Nice. And the sketches needed some help. They looked.
Did they?
They did. I will just be nice and say the sketches needed some help. And I showed them to another faculty member. They were like, golly. And I said, no, kids have been turning in sketches like that. And it's basically, the circle with a little ring around it. I said, kids have been turning in sketches like that to me for 35 years. Mm-hmm. It isn't, this group isn't anything new or unusual. And most people just have difficulty establishing the parameters and knowing where to set the boundaries. And sketching is this lovely, lovely lost art. So I didn't show them the how do you know, but I gave them the link. And I said, yeah, these are fun programs. And if you want to watch a program on this, here it is, and kids who are absent, that's where they're going to be sent. Go watch the How Do You Know program and do the activity. There you go.
Mm-hmm. I wonder how, as a percentage of population, everybody used to doodle, right?
Oh, yeah.
Add on your desk so you could doodle as you're thinking or whatever.
Right.
I wonder if people have stopped doing that in an electronic world,
I have now 2 e-ink tablets. I have a 10.3 and a 7.8. And I retired my old Kindle. My 7-year-old Kinder Voyage was getting glitchy. So I retired it for a 7.8-inch e-ink reader. And I had a 10.3 that I use mostly for notes. I've been using like Moleskine notebooks for notes for years. And every time somebody comes to my office, sign the book. Here's the day, here's the time, here's what we talked about. Give me your signature. And then last year during COVID, with no one coming to the office, I switched to the digital tablet and I found I liked it. And then I needed a new e-reader. And so I went back to the same company. I got a bigger 8-inch e-reader, which I'm liking very much. But I doodle on them all the time.
Astronomers seem to have revealed a puzzling detail in the way dark matter behaves. They found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter is a mysterious, invisible substance that makes up the bulk of a galaxy. The gravitational pull exerted by dark matter is thought to tie galaxies together throughout the universe. There is so much regular matter and dark matter concentrated in massive galaxy clusters that their gravity magnifies and warps light from distant background objects. We call this effect gravitational lensing. We can map where the dark matter is in galaxy clusters by observing how the light bends. Gravitational lensing distorts the appearance of background galaxies into deformed shapes and elongated arcs. Pictures of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter in a galaxy cluster, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside of it. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Hubble's crisp images, coupled with observations from the Very Large Telescope in Chile, helped astronomers produce a more accurate dark matter map. By measuring the lensing distortions, astronomers could trace out the amount and distribution of dark matter. This recent study could signal a gap in our current understanding of the nature of dark matter and its properties. It shows us that there's clearly a missing feature of the real universe that we simply are not capturing in our current theoretical models. With studies like this, astronomers look forward to continuing to pin down the intriguing nature of dark matter to better understand the secrets of our mysterious universe.
Well, hello, everybody. Thank you for waiting for us. I had a meeting I had to attend, but it's great to be back here with Dr. Barth. And I think we have a really, really interesting topic as well. I guess all of Dr. Barth's topics are very, very interesting when I come to think of it. I love to read the information sheets that he puts out there. And if you haven't already downloaded it, I will, in the show, I'll put a link and you can go there to check it out. But it's a great resource. And if any of you do educational outreach, you're going to want to kind of have these tools set up because these tools meet national science standards. They are, very informational, and since they're free, you can also pass them out to students. Other people that might be interested in various topics that he covers. Marking today, he's done 28 of these episodes, and there's also the book Astronomy for Educators. Now, that doesn't mean that you have to have a teaching degree, okay, to use this book. So, if you are an outreach enthusiast, you have aspirations of maybe being a NASA Solar System ambassador or an outreach person within your own club, or heck, you just like going out to, set up your telescope on the street corner and being a sidewalk astronomer. Having this arsenal of information is very, very useful. So, I find the topics that Daniel comes up with are often in sync with what I'm thinking. I mean, this happened last Global Star Party. It's happening also this Global Star Party, because before I saw your email about this particular event, the theme, okay, for the next Global Star Party tomorrow is Strange Universe. Okay, so there you go. And Dr. Barth's going to illuminate for you tell you the story of why it is as strange and maybe even stranger than we could ever conceive. So I'll turn it over to you, Daniel. Take care.
Scott, along with the strange
Getting
universe
into
theme,
unknown parts here.
we are fine representatives, I think. This whole program started out from many conversations that you and I had. And I would come up, I would see you at your store, and we would chat, and the conversations would just spin off. And at one point, I remember you said, do you have time? Come on next door, let's have some dinner. We have to get you a show because this stuff is just too good not to share.
Yeah.
And I'm like, are you sure? Well, we'll try for a while. And here we are months later, and 28 episodes, which is exciting.
Get into this very nicely, and I hope that it's rewarding for you. I know it's a big.
I love it
to be on every week. So
I enjoy it so much. I like my job training young teachers, but I must admit I terribly miss teaching astronomy and physics, and this kind of feeds that need for me. My young teachers are more interested in pedagogy than they are in the deep science. And our audience fills that empty place in my heart that's just longs to be in an astronomy classroom again. But we're going to embark on a series of programs again today. We've done this with moons and with life on Mars, and we did this with Saturn, and now we're doing this with dark matter. We're going to have a series of, I don't know, we'll see 3 or 4 programs about dark matter. Dark matter is one of the profound mysteries of astronomy today, and many astronomers have tried to solve this. We have something that's creating gravitational interactions, but we can't see it. And there are theories about WIMPs and machos and primordial black holes. So if you're into the dark matter chase, the what is this stuff has many candidates, but so far no killer experiment that has. We have some experimenters today who said they detected it, but as to what it actually is, nobody really knows yet. And so we're going to talk about this. And when we talk about this cutting edge research, one of my mentors used to say that there are really 3 fundamental precepts in astronomy research. And he said, first, everything takes longer than it does. And he said that applies to research projects, to papers you're writing. And he said it also applies to the universe. And at that time, we thought the universe was about 9 to 10 billion years old, and he was convinced that it was older. He said, no, everything takes longer than it does. That's not enough time. The second thing that my professor used to say is everything began before it did. And because we would try to pin him down and say, we want to know about this. And I learned a lot about teaching from this fellow, because he would say, well, what do we want to learn about this week? And we would shout out things, and okay, let's, and it was kind of a random drunk's walk, but it was great. That's cool. And so when we would say, we want to learn about this, he said, well, you really want to learn about this? You got to learn about that, because everything began before it did. And we're going to see how that's true tonight. And the third thing he used to say is gravitation is the fount of all creation. And we're going to see how all these 3 things fit. And for your strange universe, Scott, I'm going to gift you with a quote from British biologist J.B.S. Haldane, the fellow who did the origin of life experiments. And he said, the universe is not only queerer than we suppose, but queerer than we can suppose. And of course, this was in, I think, 1929. And we hadn't morphed to the meaning of queer yet. So right. I will beg your indulgence and just say, take into account the historical era in which it was said.
By which he meant very strange.
Yes, he meant strange. He meant strange. And, let's not be upset with him for not being aware of our current our current sensibilities.
Yes.
They are blessed who can hear their detractions and put them to mending, so Shakespeare said. Anyway, we're going to start out with Henrietta Swan Leavitt, who is not a real astronomer. And this whole talk is full of not a real astronomer people.
Oh, right. Yeah.
It's
You mean ones that actually discovered
oh yes, it's astounding how many people have made history in the science of astronomy who were not real astronomers, people who did other things for their bread and butter, and just much like you and I, Scott, had a passion for observing and understanding the universe. I make my living teaching and writing. You make your living making and selling wonderful astronomy products, but neither of us is what we would call a real astronomer. We're not on the board, and we certainly don't get regular time on Hubble or Palomar or Mount Wilson.
Yeah.
My regular telescope time is with 127 millimeter Explorer refractor, and that's my old Orion 120, and those are my regular telescopes.
There, though, that you probably spend more time with the telescope than many professional researchers do.
I'm sure I do. I know I spend a lot more. My students in the Astronomy for Educators program spend a lot more observing time than the people in the astronomy program at my university.
That's right.
They will have in their astronomy class 2 or 3 evenings a semester, go up on top of a building in a metro area where it's not, and my students come out to the ranch, which is my hilltop ranch in the Ozarks, and it's typical for us to do 35 to 40 observational labs in a semester. No one does them all. They're not expected to. I kind of offer this gigantic smorgasbord, and students have to do a select number. They can do more for bonus points if they want to. But I offer this buffet of astronomy delights, and students can do the activities they want. And anyway, we get back to Henrietta Swan Leavitt. This young woman suffered from deafness and was hired. She graduated with a degree and was hired by the Harvard Observatory. And I believe it was Pickering, the director of the observatory, who hired her. And at that time, when we're talking 1903 is when she was first hired. And at that time, they're bringing astronomy, astronomical photography is coming online. Percival Lowell is making great advances with Charles Lamplin, and these methodologies are being adopted by observatories. Harvard in particular was a big center for, they created one of the first photographic catalogs of stars and then the sky at night. Mm-hmm. And Pickering realized we're generating a lot more data than we as a small crew of scientists can analyze. And so he hired what he referred to as computers. And these people were set to measure and record and analyze the material that came out of dozens of photographic plates every night. And, we talk about this, not a real astronomer. Copernicus was not a real astronomer. He made his money, he was a church cleric, which meant he served as a lawyer, as a scribe, as a medic. He was the doctor in the monastery where he worked. But his passion was astronomy too. And one of the things that we keep on backing up, even from Henrietta Swan Leavitt, and one of the things that Copernicus said is that Earth is a planet. It goes around the sun. And people said, well, if Earth is a planet, where's the parallax? And I'm going to share a screen with everybody. If I can find my, oh, bother, where's my mouse? There it is. And I'm not seeing it on this screen at all. How strange.
You mean the share screen tool?
Yeah, I'm not, oh, there we go. There's my mouse. I couldn't find my little indicator. There we go. All right, let's try it again. Live presentation, yay.
Yes.
No, that's not the, we're not seeing the right screen. I'm going to try again, folks. This is hilarious.
I was just learning about a guy who discovered two moons of Uranus. This guy built a 24-inch and a 48-inch telescope in the mid to late 1800s. Okay,
Good God.
so he had giant telescopes he had made. This is
Must
another
have
guy
had
who was
a lot
also
of cash.
he was a merchant. Okay,
Okay.
he was a guy who brewed beer. All right, so he took his fortune that he made from making beer and applied it towards building out his observatories. So that was William Lassell.
Cool. I've not heard of him.
Yeah, William Lassell. He's worth checking out. One of the forgotten, amazing
Yeah,
astronomers.
put his name in the chat so we can all go and look him up. Anyway, if you take a look, and this little diagram is from our handout today, and we talk about parallax, and parallax has been used since ancient Greek times to measure things in the middle distance. And the ancient Greeks, the Persians, they all knew about trigonometry. And so if you have something, and I show here, there's a tree, and once again, these lovely drawings are my own. So like them, hate them, they're all me. And so we take a look at this drawing, and we're looking at a tree in the middle distance. And if we change our position, if we change and we have a baseline and we know the baseline, we can look at where the tree appears to be on a distant background. We can measure what they call the parallax angle. And with a little bit of simple trigonometry, you can get an accurate distance to that tree by watching how it changes across the background. Well, when Copernicus said, oh, gee, the Earth goes around the sun, people were quick to say, oh, well, that's got to be a pretty big baseline. So if it's a big baseline, can you see parallax? Well, Copernicus and Tycho Brahe, among others, tried to measure parallax with non-optical instruments. They were using instruments, of course, and Tycho had marvelously accurate instruments, and they were trying to measure parallax, and they couldn't find any. And Copernicus's critics, for a long time, said, well, they either said, one, Copernicus is nuts, because if he was right, there would be parallax, or they said that Copernicus is only half right, that the solar system exists, maybe Earth's a planet, but the stars are still in a spherical shell around us. And there were people who were still taking the lack of parallax to indicate that, oh, gee, the universe is not as big as Copernicus says it is. You realize, Scott, that Copernicus basically said, well, the universe is bigger than you think. The old Aristotelian idea, the Earth is in the center, then there's the sun, the moon, and the planets have their own spheres. Beyond Saturn is the sphere of the stars, literally all of them at one distance on one crystalline sphere. Beyond that is heaven, that's where God lives. And so Copernicus said, no, no, no. The Earth is a planet, the sun is a star. All the other stars are suns. That's the corollary to that. And all those other suns could have planets. The universe is a lot bigger than you think it is. And these people who come along and say, no, 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 your nice, tidy little compact universe is bigger than you think. This never ends well. Not for the people who originally say this. Copernicus was excommunicated. And we look at Copernicus and his idea, this idea that, oh, gee, all the other stars are suns. This was called the many worlds hypothesis. And the many worlds hypothesis was around from Copernicus's time. And it was actually in Galileo's time, in the late 1500s, that in fact, Giordano Bruno, Dominican monk.
Yeah, that's who I was going to bring up.
Yeah, and he says, oh, the many worlds hypotheses are true. There are many worlds, and God loves them all, and there are most likely people on all these other worlds. And what Bruno was rubbing people's noses in was Copernicus's stinky little secret that you're not very special. Right? The Copernican principle says if you think you're special, if you think you're in a special position, you have a special motion, You have special composition. You're in a Copernicus says anytime hubris crops up, you're wrong. And the Copernican principle is held up for 500 years. Bruno was saying, oh, well, you know what? There are a multitude of worlds, almost certainly peopled, and God loves them all. We're not special. And they burned him for it.
Yeah.
He would go and he would teach in a city, and he would start spouting off with his ideas. And within 2 years or maybe 3, he would be excommunicated by the local church council. He would be run out of town, sometimes literally on a rail. He would flee in the middle of the night from, people with torches and pitchforks. And he would go to another city where it's, the 1500s. They didn't, no telegraph then. So he would go and say, hi, I'm Bruno and I'm an astronomer. And he would do some mathematics and he would start teaching, and then he would get in trouble again. He actually fled from Central Europe to Padua, Italy, and he applied for the chair of mathematics at the University of Padua. But they'd heard of him by then, so they hired Galileo instead. Oh no, you're too controversial. We'll hire this Galileo fellow instead. And this was in 1592. In 1593, he's arrested for heresy. His trial and interrogation by the Inquisition lasts for 7 years.
Oh, man.
One can only imagine what kind of a horror show that was. And they ended up convicting him of many different heresies. And they stripped him naked. They cut out his tongue to keep him from speaking any more heresy, because he was absolutely unrepentant. And they stripped him naked, hung him upside down, and burned him over a slow fire. Hooray! Yeah, I know. It's kind of queasy making.
Yeah.
So, Galileo tries to find parallax with his new telescope. He can't find it. It isn't until more than 200 years after Galileo, and it's Friedrich Bessel, who has a nice refractor telescope. And in 1836, he finally finds parallax. Wow. And parallax, we find the universe is really, really big. Parallax only works out to about 100 light years. After that, the same problem that plagued Copernicus and Tycho and Galileo still plagues us. After 100 light years, parallax relies on measuring an angle. And after 100 light years, the angle is just too small to measure. Hubble can't do it. It has a limitation, 100 light years. So by the mid 1800s, people are using parallax. We can measure nearby local stars. I wonder where the idea of 100 light years as your local stellar neighborhood, parallax. And of course, the distance that comes from this, the parsec, the parallax arc second. If your parallactic angle is 1 degree of arc, then your distance is a parsec, a parallax arc second, and that's about 3.6 light years. And that's where that measurement comes from. Well, we come back now after all these other people have muddied up our drama to Henrietta Swan Leavitt. She's measuring the brightness of stars, and she's doing some investigations on her own. And she's measuring the period of variable stars, these newly discovered Cepheid variables. Cepheid because they were discovered in the constellation Cepheus. If you go out and look in the northeast tonight, just after sunset, Cepheus will be there. It's nice and bright, looks like an ice cream cone, and it's to the left or west of Cassiopeia. Everybody knows the big W of Cassiopeia. Constellation over to the left is Cepheus. And she's observing the Cepheid variables, and she plots the log of their periods and finds out the period and the log of the period and the brightness, the absolute brightness, make a perfectly linear relationship. And so Henrietta Swan Leavitt discovers the first standard candle. And this is something scientists were looking for a long time. The idea of stellar magnitudes dates back to Hipparchus in the 6th century BC in ancient Greece. And scientists knew by the 1850s and certainly by the early 1900s that in fact, there are different kinds of stars. They have different intrinsic brightnesses. But the relationship between temperature, brightness, size, all these things were not ironed out yet. And what we could do parallax out to 100 light years, but the problem is we could see a lot farther than that. And if we could just find a standard candle, and the idea, of course, Scott, if you have something of a known brightness, that's your standard candle. And if you know how bright it actually is, what we call its inherent brightness or absolute magnitude, then you can look at its apparent magnitude. How bright does it look to you? If we think about an oncoming motorcycle with a single bright headlight on it, we can hear the motorcycle and we can look down the road and we can see how bright the headlamp appears to be. Assuming that it's functioning properly, the brightness gives us a pretty good idea of how far away it is because we know how bright motorcycle headlights are. Same thing with car headlights. We can actually do parallax with car headlights because there's usually two. But this idea of a standard candle, Henrietta Leavitt discovers this in the idea that the brightness of a Cepheid variable relates to its period, called Leavitt's law. And she continues to work on this. The brightness distance relationship, she says, I found a standard candle. She publishes. And Pickering encourages her to publish, which is a wonderful thing. A lot of bosses would not, in the 19 teens, have encouraged a woman to publish in a scientific journal. He kind of backs her and says, no, you should pay attention. This is good stuff. He doesn't steal the credit. He encourages her to publish under her own name, which in the 1920s is and this is actually the 19 teens, a very rare thing at the time. And so this brightness distance relationship, other scientists look at this and they're very excited. The standard candle idea will let you see how far something is away, much more distant than the parallax does. And now, instead of having to measure the parallactic angle, all you have to have is a telescope big enough to see your standard candle. If you can see it, in other words, if you can get a telescope that's big enough. And so in part, Henrietta Swan Leavitt, her work and Leavitt's law ushers in the era of really big telescopes. Because you realize that having a bigger telescope doesn't guarantee that you're going to see more. When Galileo invented the telescope, it was a reasonable possibility that, in fact, instead of seeing more, he would just see the stuff you could see with your naked eye, but up close. Galileo found when you turn the telescope on the sky, you didn't just see what you knew was there. You saw what you didn't know was there. You got to see more of the universe. And Leavitt's law now gives us a way to see and measure distances if we only have a telescope big enough. And so the whole era of big reflectors kind of is launched during the period serendipitously with Leavitt's law. It was none other than Einar Hertzsprung of HR diagram fame. He confirms the brightness distance relationship, and Leavitt's law becomes a thing. And so, wow, this is an amazing thing. Henrietta Leavitt dies of stomach cancer in 1921. And just a couple of years, her work is actually being used by Edwin Hubble in her lifetime, but she dies before Hubble's announcement in 1921 that, in fact, the Andromeda Nebula and the Triangulum Nebula are not nebulae at all. They are island universes. They are galaxies. And so we come to Edwin Hubble. And Edwin Hubble's part of the story is it's bigger than you think. Like Copernicus, Hubble begins his work looking at how big is it? How far away can we see? He comes online at Mount Wilson in 1919 during Henrietta Leavitt's lifetime, just when the 100-inch Hooker telescope comes online. It is at that time in 1919 the biggest eye in the world, and he's trying to look for the farthest standard candle he can see. And so he says, let's look at these nebula. Now, the idea at that time that the Andromeda Nebula was a star cluster of any sort was very speculative. There was no evidence for that. No one had been able to resolve a single star inside the Andromeda Nebula, unlike Orion's Nebula, where we can actually see stars inside. And people said, well, we don't know what it is. It's just this fuzzy nebula, and it's in our galaxy somewhere. And Hubble had this idea that maybe if we have a big enough telescope, we can resolve individual stars inside. The 100-inch hooker was the instrument for that. He begins his work in 1919. He's looking for Cepheid variables. And by 1923, Hubble is using Levitt's law. He's detecting Cepheid variables. He's measuring their period. He's getting, of course, their periods measured accurately over a period of months. And then he's going ahead and applying Levitt's law. And the first calculation for how far away is the Andromeda galaxy comes out over 1 million light years away. Now, at this time, 1923, the idea that the Milky Way is the universe is the prevalent scientific conceptualization of the day. Einstein believes it, Eddington believes it, all the leading astronomers of the day. The Milky Way is the universe, and there are nebulae within it, but that's all there is. And with Levitt's law, we're able to estimate the size of the Milky Way at about 100,000 light years. That's how big the universe is. And then Hubble comes in with his big 100-inch hooker telescope and says, no, it's bigger than you think.
Bigger. Way bigger.
Way bigger. So if indeed the Milky Way is 100,000 light years, and then, oh my gosh, then Andromeda is at least 100 times farther than that. And Hubble comes in and says, you know, all these spiral nebulae, they're all galaxies. And so the hunt is on, and Hubble kind of explodes the size of our universe. He blows it up. And of course, this again isn't a happy thing. And Hubble's work is initially discounted. Again, we've talked about these ideas that people come up with on very thin ice. We've talked about Percival Lowell. We've talked about Cassini and the moon Iapetus and all these other things. And so Hubble's work, everybody who looks at it says, ew, I don't like it. Einstein doesn't like it. Eddington doesn't like it. All these scientists are like, I'm uncomfortable with this. You mean the universe is, you know, the nearest other thing is 100 times farther away than we thought the universe was big, and potentially the universe is millions of times larger than we thought. It gives everybody the queasy wobbles, and they don't like it. Now, Hubble continues his work on galaxies through the 1920s, and with the Hooker telescope, he's able to measure spectra. And he comes up with his, of course, Hubble's law, which is, gee, I can measure redshift. Redshift measures motion. And we have another rung on the distance ladder. So we had parallax, and then we had the standard candle of the Cepheid variables. And now Hubble says, now redshift. If we have a telescope big enough, and remember at Hubble's time, getting a spectrum was not an easy thing. No computerized tracking, no digital sensors with specialized sensitivity. You couldn't just dial up the ISO. You were using film plates and actual diffraction gratings and prisms to get spectra. It took many hours of exposure because galaxies are faint.
Yeah.
And so I'm not sure. Do you know, did Hubble ever do multiple exposures? I know at the time, the German expressionist director Fritz Lang was pioneering multiple exposures on film.
You mean like taking
the plate, exposing it, covering it up, coming back the next night, and opening it up again?
I do not know. But I would say by the time they get to the 100-inch telescope, they had already spent quite a bit of time on both the 40 and the 60. And certainly a lot of astrophotography was done on the 40-inch, and you can go in the plate vault there and see tons of stuff. But it's on the 60 that astrophotography got put on steroids. Okay.
Okay.
And so I think that probably by that time, the technique of waiting night after night to continue to expose, but because also during those times the sensitivity of those plates was so low.
Oh, very,
very low. So
do you remember hypering film?
Yes, I do. So
for those of you,
that discovery plate that Hubble did, okay, with the VAR written on the plate and everything, that was one single 45-minute long exposure.
Okay.
And compare that image to an amateur's image today.
Absolutely.
That would be 45 minutes long. Maybe there were 2 minutes sequentially stacked images, 45 minutes worth of them.
Right.
The amount of detail is vastly more improved.
Oh, yes.
But the stars, because of the resolution of the 100-inch, the stars are bigger because it can't resolve them down as fine as the 100 would. And so that was what made it, that combination of this longer exposure, and the resolution is what allowed Hubble to actually see that, okay, yeah, there's a star here and it's a variable. He thought it was a nova to begin with.
Right.
And so but from what I understand, he didn't take a bunch of exposures to find that it was a variable. He went to the plate vault, looked and go, oh, wow, this star goes
up and down over time.
So, and I don't know that he actually did the work of saying, okay, this is a variable star, but he knew where to look. And
he knew where to look, where to mine the data.
People working with him, which might have included Humason, and then maybe some other, probably women working as computers.
Probably. At that time, I would certainly think so. And so it's time to toss another I'm not an astronomer guy into the mix.
Okay.
Georges Lemaître, who's a Belgian priest. And he works for, among other things, he works with the Vatican Observatory. And he's a mathematician. And he epitomizes all about cosmology that later cosmologists like Jim Peebles and Robert Dickey really hated, because Lemaitre was trying for a unification of religion and science. And so we talk about people who come up with ideas on thin ice, like Hubble with 23 galaxies and Cassini with Iapetus's dark face. And so Lemaitre tops them all because he comes up with theories with no evidence at all. He is a pure pencil and paper theorist. And he met Einstein a number of times. He works with relativity in the mathematics. He comes up with some of the first nice discrete solutions to Einstein's field equations. And Einstein was very impressed with him. And people now, we find that Lemaitre publishes a paper about almost 2 years, 18 months to 2 years before Hubble. And he says that, if the universe is in fact expanding, and he finds a solution to Einstein's field equations that said, yeah, the universe can be expanding, contracting, or if you fiddle with the numbers, it can be static. Einstein introduces the cosmological constant and says, I don't like the idea of it expanding or contracting. The universe just should be. God doesn't make mistakes. Einstein's sort of on one side theologically, and Lemaitre says, no, it can be expanding, but if it's expanding, there should be redshift. And so he writes this speculative paper that says, if the universe is expanding, there should be redshift, and redshift should be proportional to distance. And he doesn't quite express it that way, but there are people who refer to Hubble's law as the Hubble-Lemaitre law. Notably our friends in the IAU. And basically, he publishes this speculative theory with no data at all. And when he publishes it, everybody boos. Everybody says, no, come on. You're mixing theology with science, and there's no evidence for this, and you're babbling. And Einstein doesn't like it. Bohr doesn't like it. Nobody likes it. And he says, well, but then Hubble comes out and people are like, wait, wow, didn't that funny little Belgian fellow say this before? And maybe there's data for it now. Well, Hubble is publishing and doing his work, and he comes up with the expanding universe by 1929. So with the expanding universe now on a firm scientific footing, 1931, Georges Lemaître is at it again, and he says, well, if it's all expanding now, it had to be all more compact in the past.
Right.
And he says, if it's expanding, and we run the film backward, and he comes up with the idea of primeval atom. And for Lemaitre, and it's clear in his publication, he's looking at this theologically. And he describes this as a creation event. Let there be light and all of that. And so Lemaitre is saying, this is a creation event. There was a primeval atom. Everything that exists is within that atom. And then it's a lot of stuff to have just in one place. And so it explodes. And he's very much a Catholic, and he's looking for scientific evidence of a creation event. And nobody likes this idea either. Notably, Fred Hoyle, the British astronomer, is very skeptical, and he says, and it's on a BBC program in 1949, and Fred Hoyle says, somebody asked him about the primeval atom, and he says, yes, well, that Belgian fellow and his big bang, everything just explodes at once. And kind of to Fred Hoyle's lifelong horror, the name stuck and everyone just adopted it. And so at this point, Hoyle's like, no, this is wrong. And we have a steady state universe. And it's kind of an odd, you're familiar with steady state idea, Scott. And Hoyle basically said, well, we have an expansion at this rate. And so all you have to have in a volume the size of our solar system is a few hydrogen atoms popping into existence every year. And that's plenty to fuel the cosmic expansion. He says, all you have to have is a very tiny amount of creation steadily over time, and the universe is now isotropic, meaning it looks the same from every direction. It's homogeneous, meaning it's the same no matter where you look. And it is steady over time. It is unchanging over the eons. And so he goes back to where Einstein started, with the idea that the universe has been and always will be worlds without end. Amen. And so the steady state idea is the alternative to Lemaitre. But again, we're having an echo of the argument between Copernicus and Aristotle. And the problem in Copernicus's time, and for some 70 years after his death, there was Copernicus's heliocentric theory, there was Aristotle's geocentric theory, but there was, in fact, no definitive experiment to test between them. And we've pointed out many times that if it's to be an actual scientific hypothesis, it must be, in fact, testable. Otherwise, it's just a speculation. And so we have Lemaitre making speculations. We have Fred Hoyle making other speculations. And okay, how do we test this? Well, through the 1950s, no one can come up with an idea. Nobody comes up with a successful test, but in the early 1960s, two Princeton physicists, Robert Dicke, who is the senior fellow there in Princeton. He runs the astronomy and cosmology program, and his young student, James Peebles. Jim Peebles is just starting out, and he's kind of a mathematician. He's another, I'm not an astronomer, but he finds that he is attracted to these talks, and he switches over to cosmology, even though he's kind of frustrated with cosmology because he says it's full of metaphysical arguments in religion. Cosmology, anytime you can't come up with an answer because God wanted it that way, seems to be Peebles' gripe about this thing. And Robert Dicke challenges him, well, find a test and let's put it on a scientific foundation or throw it away. And so they bang about the idea, and Dicke gives Peebles this challenge. He says, find a way, if there was an explosion, there should be a way to detect the remnants of it today. What would that look like? How would we search for it? So Jim Peebles says, gosh, okay, I'm going to, from first principles, calculate, here's how many galaxies I think there are, here's how much the universe weighs. I'm going to shrink it back and say if it exploded, and if it's at this time, they think it's about 9 billion years old. So if it exploded about 9 billion years ago, well, how big would the universe be now? And anything that's hot, as it expands, cools off. And so Jim Peebles comes up and he says, you know, this original remnant has to be an equivalent temperature of 10 degrees Kelvin or less. We talk about this idea because everything that's hot generates radio waves. The radio frequency and wavelength depends on temperature. And so if you can measure the wavelength, you can calculate the temperature. And Jim Peebles said we should be looking for something 10 degrees Kelvin or colder. And it's good news because at least it's detectable. We know how big these waves are. They're microwaves basically. And but nobody knows how do you make an antenna? How do you make an antenna to detect this? Because now radio astronomy is coming into its own. People are using radio antennas. They're looking into the center of our galaxy, Sagittarius area. Why? Because it's really hot. There's a lot of radioactivity. It's radio bright. And they're saying, well, this is an interesting idea. So we cut to another group of I'm not an astronomer, Arno Penzias and Robert Wilson, and they're working for Bell Laboratories. And Bell Laboratories in the early 1960s are working with the Vanguard program. They're working with the Telstar program, basically early communication satellites. And we don't have a global net like GPS. And so their brilliant idea, we're going to get a 100-foot weather balloon and we're going to cover it with aluminum. We're going to cover it with aluminum paint and we're going to send it up into the stratosphere, a tethered balloon. And we should be able to bounce radio signals from the satellites from over the horizon, right? This is basically our reflector in the sky. And we should be able to aim our antenna at this giant balloon. And they run through the Vanguard program and the Telstar program, and their research ends. And they say, well, we have this cool antenna. What can we do with it? And their idea is, let's do some radio astronomy. So they start looking into the antenna, and they realize the thing works okay, but there's a hiss. It's like an old-fashioned stereo system. There's a hiss. And they're like, well, the hiss is no good. We have to get a clean signal. If we're looking for radio signals from the edge of the galaxy instead of the center, we're going to need very clean signals and noise. And so they're like, well, what's wrong? Well, they look at the design. They don't see anything. They hook up a cold load, which should eliminate the hiss, but it doesn't. They go out and check the antenna. There's some pigeons living in it. They evict the pigeons and they scrub the guano out of the antenna. This thing is like 40 feet long. The pigeons, by the way, they don't kill them. They take them about 50 miles away and release them, and they come back in a couple of days. They're homing pigeons. Of course they are. They say, well, our aluminum antenna is built with steel rivets. They get aluminum tape, like you use to patch roofs with, and they put aluminum tape over all of the rivets. Still the hiss. They take the antenna apart. They clean all the joints. Maybe it's some dielectric effect. They scrub all the oxidation off. They dielectric grease. They reassemble it. The hiss won't go away. They say, well, maybe it's a seasonal thing. They try aiming different directions at the sky. East, west, north, south, every angle up to the zenith. The hiss is there.
Right.
Well, does it depend on temperature? No. The phase of the moon? No. The season? No.
It's driving them crazy.
And they can't get rid of this thrice be damned hiss. So finally, in 1964, Arno Penzias says, you know, I've heard of this guy, Dickey. He's over at Princeton. He's only a few miles away. Let's call him up. And so Arno Penzias and Robert Wilson call up Robert Dickey, and Dickey is in his office with Peebles and some other people. And they go over the whole thing, and they say, we found this hiss. Well, what's the frequency? And Peebles does the calculation on the back of an envelope, and he says 3 degrees Kelvin, plus or minus 1. It's within his 10 degrees or less prediction. And they talk for a while, and Dickey hangs up the phone, and he looks at his graduate assistants, and he says, well, boys, we've been scooped. So they go out to the Bell Labs, and they look over the antenna, and they look over all the data, and they go, nope, this is a real thing. And so they show them their theoretical research, the cosmic microwave background. And the two groups decide, we're going to publish together. This is beautiful serendipitous work. So we're both going to publish, and Penzias and Wilson will publish on their data of the cosmic microwave background, and Dickey and Peebles et al. Will publish a paper on their Peebles theoretical prediction of the cosmic microwave background, and they're going to come out in the same issue of the Astrophysical Journal. And in fact, the reviewer holds up Robert Wilson's paper and says, no, you've cited these other things wrong. You need to do these rewrites. And he keeps asking for rewrites. And it eventually delays the publication of Dickey and Peebles' paper. And so Arno Penzias and Robert Wilson published first because their plan to publish simultaneously is foiled. And sure enough, in 1978, Penzias and Wilson are awarded the Nobel Prize for discovering the cosmic microwave background. And Robert Dickey and Jim Peebles get to talk about the one that got away. So we have this wonderful thing now. Oh, there's a cosmic microwave background. We've actually got data. The Big Bang is a thing. Steady state is not, because steady state predicts no background noise. And other people confirm it. And wow, everything now seems to make sense. We had a primordial atom. It exploded. We had a Big Bang. We've got this radiation. We can detect it. It's smooth and homogeneous everywhere. All we need to do is, tidy up the decimal places and neaten up the corners, and we're done. But of course, the history of all science, Scott. Every time people say, oh, science is finished now, all we have to work on is decimal places, Copernicus slaps you in the face with a wet mackerel and says, no, you're wrong. And they were wrong. There was something lurking, unseen in the darkness. And another not an astronomer was the first to find it, and we're going to tell her story next week.
Wonderful. What an adventure.
I
love this.
It would make a great detective story.
Yeah, it does.
It does. You would have to have a detective who lived to be hundreds of years old, but it makes this thrilling chase. And for our readers and viewers who want to take a look, the 4% Universe by Richard Panik, and it's on Amazon. I know it is, so you can look that up.
Yeah,
and that's one of my primary sources, not scientifically, but Panik just does this lovely, lovely job of laying out all the evidence for you and makes it very comprehensible without being too technical. It's a brilliant book. It's really well done.
It's only $11. So
It's $11. That they have it. I'm sure that's
amazing amount of-
paperback. Yeah.
Yep.
There you go. I'm sure
There you
there's
go.
probably a Kindle edition and everything else.
Mm-hmm.
Yippee-ki-yay. So there you go. And there's a whole, if you scroll down in the, there's a whole list of links about all the people in our story today. Henrietta Swan Leavitt, Stellar Parallax, Edwin Hubble, Giordano Bruno, Georges Lemaître, Fred Hoyle, Arnold Penzias, and Robert Wilson. So I put links for all of them, and they're general reading links. I went to nobelprize.org for my stuff on Penzias and Wilson, and it's really, it's a bit skewed. They're a bit biased, but that's okay. They're allowed to be fans of their own awardees.
Sure.
So there you go. And I hope everybody enjoyed tonight, and we'll look forward to seeing you next week for Dark Matter Part 2. And it's the story of, should I tell or should I let people know? A lot of people probably know already. It's the story of Vera Rubin. And Vera Rubin said, Kepler's wrong. It's faster than you think. And so we'll hear her story next week.
Awesome. Great. Well, thank you very much, Daniel. This is a great romp through the universe, the expansion of the universe, and basically just another great story of how little we really do know about the universe. And this adventure is not over, by the way.
No.
It's still very.
If you think so, you're wrong.
Yeah.
Copernicus said it. I believe it. That settles it. WAP.
Right.
Copernicus is ready to biff you on the back of the head and say, no, you're wrong.
You're wrong.
The story's not over. And amateurs, and I'm not a professional astronomer people continue to make discoveries every year. And it's dedicated, passionate observers like our viewers and like, telescope owners worldwide.
That's right.
Whose relatives probably don't
all
understand.
Of you that are amateur astronomers. I mean, you're part of this fraternity that's been going on for a long time. Okay. A long time. And so, because all the people that Daniel just mentioned were amateur astronomers.
Yes.
They weren't paid.
That's a brotherhood, sisterhood, familyhood that's gone on for many millennia.
Yes.
Probably at least 50 millennia. So to be part of something that's been around for 50 to 100 millennia is just stunning to me. Just gives me shivers every time I go out in the dark and look up. And I think, oh, what a part of a great history am I, just going out and looking up.
That's right.
It's wonderful.
And you too. So, all right. Well, you guys, thank you so much for watching. Thanks for all your great comments today in chat. And we will, for those of you that couldn't make it towards until now, we're saying hello, but certainly watch this program and rerun, and because I think you'll find it fascinating. All right.
On YouTube, and I always post a link to each week's show on the Astronomy for Educators Facebook page.
That's right.
Link to the shows there every week. And thank you again, all the folks who tune in regularly for your comments and support. Really, it means loads. Just the idea that I get to come hang out with friends and do this thing we do is just such a thrill. I enjoy it.
Thanks, Daniel. You take care, man.
All right. Bye-bye, Scott. Bye-bye, everybody.
Bye-bye, everyone.
Hi everyone, this is Terry Mann, and I'm the Secretary of the Astronomical League and the co-host of Astronomical League Live. We have a special event coming up on October 15th at 7 p.m. Eastern Daylight Time. We're going to have a kind of Halloween party online. We have quite a few speakers. The first one is one of our regulars, one of our favorites, David Levy, and he will be doing celestial incantations. Next up, we'll have Mary Stewart Adams, Passing Between the Worlds Under October Skies. We've also got Astro Bob, Black Holes Where Matter Goes to Die, and Molly Wakeling, Spooky Nebula of the Night, and John Goss, the Master of Lunacy, and we do expect that name to stick. Barbara Harris, Algol, the Demon Star. Myself, Aurora, Soul of the Night. And we've got Carol Orge, the president of the Astronomical League. We're going to put a wizard hat on him and let him work his magic. So please let me personally invite you to join us October 15th, 7 p.m. Eastern Daylight Time, right here. We hope to see you.
Why do we chase this thing? Jumping from one continent to the next, just to bathe for a moment in the absence of light? Who are we? What are we searching for?
T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time."
One of the qualities of seeing an eclipse is it makes you understand that every given thing is in a particular patterned relation with every other thing.
It gives me a sense of scale, gives me a sense of where I fit into the universe.
It is art, it's poetry, it's this kind of experience of going and seeing totality in which what feels merely metaphorical is suddenly experiential encounter.
Immediately afterwards, you have that overwhelming desire to see another one. That's the moment an eclipse chaser is born.
These are folks who are running all over the world for this event that lasts all of 2 or 3 minutes. Who are these people?
It's unique each time, and therefore that freshness, even if we've seen it over and over again, oh my gosh, it has the potential to re-inspire us.
A total eclipse of the sun doesn't just unfold in the heavens. It transforms the minds and hearts of those who experience it firsthand. The same is true of journeys to the most remote regions of our planet. Whether we're standing on a mountain peak or in a stark polar landscape, we can't help but reflect on our place within the larger scheme of things.